All right, have your data booklet open to page 5. We're in subtopic 2.3, work, energy, and power, but today we're only going to focus on energy and work. Work, W is equal to F, S cosine theta, where F is the force, S is the displacement vector, and cosine theta is the angle between the force and the displacement. We have E sub K equals 1/2 mv squared. This is the kinetic energy, that's the energy of motion, equals 1/2 times the mass times the velocity squared. E sub P, this is the spring potential energy or the elastic potential energy of a spring. That is equal to 1/2 K delta X squared, where the delta X is the distance the spring is from its unstretched length. And then the change in the gravitational potential energy, again, it's E sub P, but this is not to be confused with elastic potential energy, is equal to mg delta H, where H is the change in height. Okay, so work is force times displacement over which the force acts. Work is equal to F dot S. The units of work are the units of force, newtons, times meters. So 1 newton meter is equal to a joule. This is the derived unit, and for work, that's the joule. Here, James Prescott Joule is up there, and that is equal to a newton times a meter. So let's say the force applied is not totally parallel to the displacement. So then we have to analyze how much work is done by comparing the angle between the force applied and the displacement vector. This is taking the dot product, F dot S. This is the dot product. So when you take the force vector times the displacement vector, the cosine theta between those two, this work is a scalar quantity. So energy is a scalar. It doesn't have any direction. If the force applied and the displacement vector are parallel, theta equals 0 degrees, and cosine of 0 degrees is equal to 1. So you get maximum work done. If force and displacement vectors, if they are anti-parallel, theta is 180 degrees, and cosine of 180 degrees is negative. That means that the force applied goes in the opposite direction of the displacement vector, so negative work is being done. This is not to state that work has a direction. It doesn't. It's energy. It just means that this force is doing something to reduce the amount of energy the object has. We don't cover, or you're not given Hooke's law in the data booklet, but it's a shame, and you should definitely add it. Springs move in the opposite direction of their displacement, or they try to. So if you stretch a spring, you can feel that that spring is trying to pull back in. If you compress a spring, like push the spring in, the spring tries to push your hand back out. This is Hooke's law. F is equal to negative Ks. That negative sign implies the opposite direction between the spring force and the displacement of the object attached to the end of the spring, or the displacement of the spring itself. Force is in newtons, and S, that's the displacement vector, is in meters. And the units for the spring constant, that's that symbol K, are newton per meter. K was also seen in the data booklet, where we had the elastic potential energy of a spring, E sub P, is equal to 1/2 K delta X squared. Well, this K value is the spring constant. Its SI units are newton per meter. The area under a force versus displacement, or a force versus distance graph, is work. So I do want you to copy this. If we had force on the y-axis, the units, the SI units, would be the newton. And I have displacement, or distance, on the x-axis, and the units are meter. If I take the area, or find the area under the curve, which is the area between the line and the horizontal axis, always, I would multiply this area would have a shape. This shape is a triangle, and so the area under this curve would be equal to 1/2 base times height. My base is displacement, or distance. The height is the force in newtons. So the units, if I multiplied a newton times a meter, that is those are the fundamental units for work. A Newton times a meter is a joule. So you need to start letting the units for your graph be your guide or help you to determine what the area under the curve would be, or the slope. In this case, a Newton per meter. The slope of this graph would be the spring constant. Kinetic energy, in this case we're just talking about translational kinetic energy. This is the energy of motion. The bigger the speed v, the bigger the E sub k, the kinetic energy. The bigger the mass, the bigger the kinetic energy. So E sub k is 1/2 mv squared. And we can analyze these units. A kilogram meter per second squared, a kilogram times a meter per second, and you square that. So I've taken these, the mass unit here and the speed unit. This becomes kilogram meter squared per second squared. This is a kilogram meter per second is another unit for a joule. Look at this. This is kilogram meter times second squared times a meter. This part right here happens to be the SI unit, the fundamental units for a Newton. So a joule equals a Newton meter. So we have gravitational potential energy, and let's say we put a bowling ball on the floor. It stays there. Lift it to some height and release it. It speeds up, gaining kinetic energy as it falls. So we can lift this up and then release, and bam, it falls to the ground. We lift this object up, and we do work against gravity. So we have the work done in lifting this up is equal to the force applied, in this case the object's weight, times the displacement vector cosine theta. Here we have a free body diagram of the ball. We can see the force that we apply in lifting this must be equal and opposite to the weight vector. And in this case, the displacement, the change in height, is just delta H. Cosine theta, if we lift this ball up, the force applied goes up. The displacement vector while we lift is pointing up. So the angle between these two vectors is 0 degrees. So the energy due to the position of a weight is the gravitational potential energy. Delta E sub P is equal to mgh. And notice when you lift that bowling ball up high, you imbue this bowling ball with gravitational potential energy. When you let it fall, at the moment it hits the ground, all of that gravitational potential energy has become kinetic energy. Now, all of that gravitational potential energy becomes kinetic energy if there is no air resistance or no external forces acting on the system. You need to copy this equation down. This is very important. This is the equation for conservation of energy. What it tells us is that in any system, the change in kinetic energy plus the change in potential energy, this is gravitational potential energy, equals 0. This is known as conservation of mechanical energy. In fact, it goes even further, because any type of mechanical energy, if this was kinetic energy, which it is, if this is gravitational potential energy, or even a change in elastic potential energy, you would sum these energies up, the change in these energies for whatever system, and you set them equal to 0. What this unaltered equation, this change in kinetic energy plus the change in gravitational potential energy equals 0, it essentially says that if the kinetic energy changes, let's say it increases, then the gravitational potential energy has to change also, and it decreases in such a way that the total change in energy is 0. So if I were to say that, okay, the change in kinetic energy for the bowling ball as it falls from some height down to the ground, it experiences a positive change in its kinetic energy. At the top, it was at rest. We dropped that bowling ball, so initially it was at rest. It hits the ground with some speed. That is a positive change in its kinetic energy. But this bowling ball experiences a negative change in its gravitational potential energy. It decreased is gravitational potential energy as it fell, as it moved from its high point down to the ground. So this is essentially the first law of thermodynamics. Total energy of a system never changes. We have to modify that conservation of energy equation, though, if there are external forces, any type of push, any type of pull, even if it's going in the same direction as the object. If any type of force is acting, then we treat that as work done. In this case, we modify the equation. We still have our change in mechanical energy, delta E sub K plus delta E sub P, but you will always subtract the work done by external forces. Exclude the spring force because that work gets taken care of in the change of elastic potential energy of a spring, but you will always have a positive change in E sub K plus a positive change in E sub P minus what the work done by any external force, and you set that equal to 0. Your change in potential or your change in kinetic energy may still be negative or positive. It just depends on what's happening in the situation. But you will always first start with them positive in this generic equation. This is our just generic equation. You follow this format and you will change the signs of the delta E sub K and the delta E sub P as needed. And the work of friction, the work done by any force, that sign will also change depending on the direction of the force and the displacement vector. Let's do a quick example. A 0.045 kilogram feather is dropped from a height of 250 meters. Air resistance acts on it immediately, and assume this air resistance is constant. If the feather hits the ground at 5 meters per second, what is the force of the air resistance acting on the feather? So to solve this problem, we can use our generic conservation of energy equation, which states that the change in the kinetic energy of the feather plus the change in the gravitational potential energy of this feather minus the work done by any external forces, in this case the force of air resistance, which I'm going to call drag, minus the work done by drag, set that all equal to 0. I will expand now on this change in kinetic energy. This feather is dropped from a height. So, I guess I want to use a different color. So this change in kinetic energy is EK final minus EK initial. And initially, the feather is dropped, so it has no initial kinetic energy. That's 0. I will add the change in gravitational potential energy. So that is EP final minus EP initial. Well, and when the feather hits the ground, it has no more gravitational potential energy. So this is 0. And then minus the work done by drag or by air resistance, I'm just going to add that to the other side of the equation, and I'll set this all equal to the work done by air resistance or the work done by the drag force. So I'm left with EK final minus EP initial. All of that equals the work done by air resistance. All right, so let's make some space. I'm going to rewrite this equation up top side. Hopefully you've copied everything down. If not, just go back, rewind the video. EK final minus initial gravitational potential energy should equal the work done by the drag force. Okay, clearing this out. Let's plug in with our values. EK final, that is 1/2 mv squared. 1/2 the mass of the feather, which is in SI 0.045 kilograms, so I do not have to convert, times its final velocity squared, that's 5 squared. Subtract the initial gravitational potential energy, that is the mass of the feather, 0.045, times the acceleration of gravity, 9.81, times the initial height of the feather, 250 meters. Let's calculate. So this final kinetic energy, I get 0.5625 joules minus the initial potential, the initial gravitational potential energy, which is 110.36 or so, 110.36 joules, and we set that equal to work done by drag. And then this becomes, the difference between the two is negative 109.8 joules. That's the difference between the final kinetic energy and the initial potential energy. That is equal to the work done by air resistance. So I need more space. I'm going to erase everything at the top, and let's get this force of air resistance, the force exerted by the air on this little feather. Clearing this out, clearing this out. Okay, negative 109.8 is equal to the work done by air resistance. Negative 109.8 joules is equal to the work done by the drag force, or by air resistance. It's interesting to note that as the feather falls, this is a very important step in solving the problem, its displacement vector points down. That's the displacement vector. But air resistance points upwards. This would be the drag force. Label that D. So the angle between these two, the displacement vector of the feather and the drag force, this is 180 degrees between them. So if I expand on the work done by drag, I get that the force of the air resistance, or the drag force, sorry, I'll use capital D for this since I did that up there. So the drag force times the displacement times the angle between these two times cosine 180 degrees. Cosine of 180 degrees is -1, so this equation becomes negative 109.8 times a negative drag force, which is my unknown, times the displacement. Now, when it comes to forces and work, we no longer follow the kinematic Cartesian coordinates. It doesn't matter. I'm just focused on, I'm letting the angle between my displacement vector and my drag force tell me if it's negative or positive. So I'm just going to put in a value for the displacement, 250 meters. I will ignore the typical Cartesian coordinates. You'll only do that for kinematics. And so now I can get the drag force, the negative signs cancel. 109.8 divided by 250 tells me the drag force. I will divide by 250 on both sides. My negatives again canceled, and the drag force is equal to 43.9 newtons. 43.9 newtons is equal to the drag force, or is equal to air resistance. Finally, this is the last point made in this video. We have energy versus time graphs. And so if we plot kinetic energy and potential energy versus time for a system like a swinging pendulum or a spring as they oscillate, what we get is a change between the kinetic energy and the potential energy. So over time, you get kind of like this sinusoidal looking function. Whereas the kinetic energy increases, the potential energy decreases, and vice versa. And it's not a linear decrease, and that is because that the kinetic energy has this velocity term, which is squared. So it makes this nice sinusoidal pattern, and it's only for energy versus time. And this is the end of the video, so thanks for watching and study well.